And when the vector traveled around the area in the clockwise direction, the vector rotated clockwise. If the vector rotates in the same direction in which it is traveling, we'll refer to this as positive curvature. If the vector rotates in the opposite direction in which it's traveling, we'll refer to it as negative curvature. An example of negative curvature is a saddle point, such as the region colored in green. The sphere had the same curvature at every point. On the other hand, this surface has a different curvature at every point. We can refine our definition of curvature by defining the curvature at each point in terms of the amount by which the vector is rotated, divided by the size of the area as the size of the area approaches 0. The curvature at each point is signified by the scalar variable r, which is one of the terms of Einstein's field equation. Though this should not be confused with the tensor variable that has an r with 2 index values. This tensor variable is also related to curvature, but it represents 16 different numbers at each point in space-time. The other two tensor variables in Einstein's field equations also each represent 16 different numbers at each point in space-time. At each point in space-time, the relationships between all of these different tensors must be as is specified by the equation, regardless of what coordinate system we use. But the individual values of each of the tensor components strongly depends on what coordinate system we select. In order to simplify the following explanation, let us assume that we are not dealing with 4-dimensional space-time, but just 2-dimensional space. Suppose we zoom in close enough for us to be able to approximate this region of space as flat. Keep in mind that the 1 and 2 are index values, not exponents. We want to know the length of the white arrow, but the yellow and red arrows are not 90 degrees to each other, so we can't use the Pythagorean theorem. Instead, the length squared will be given by the following equation. We can extend this concept from 2 dimensions to higher dimensions. When dealing with 4-dimensional space-time, this does not calculate spatial length, but what we call the space-time interval. In special relativity, the space-time interval was defined with the following equation, which is the quantity all observers can agree on. In general relativity, this equation is no longer necessarily true due to the curvature of space-time. Instead, we calculate the space-time intervals inside each exceedingly small region using the tensor shown, which we call the metric tensor. Let's now focus on the tensor with the r. We will first show what this tensor means in 3 dimensions, before moving on to 4 dimensions. We have a coordinate system, and the basis vectors are not necessarily all 90 degrees to one another. As always, keep in mind that the following numbers are index values, not exponents. We're going to parallel transport the white vector around this exceedingly small parallelogram. If we're in a flat 3-dimensional space, the vector will still be pointing in its original direction when it returns to its original position. But if we are in a curved 3-dimensional space, then this is not necessarily true. To know how much the vector has changed, which means that we want to know dv1, dv2, and dv3. These quantities will be proportional to the product of the lengths of the 2 sides of the parallelogram, multiplied by some other terms. These other terms will be a linear combination of the components of the white vector. For the missing terms in the following equations, let us invent a new variable with the letter r. But it will be different from the variables with the letter r that we saw before. This new variable will have 4 index values. The top index indicates which component of dv it is calculating. The first bottom index indicates which component of v it is multiplying. And the last 2 bottom indexes indicate the 2 dimensions for the lines of the parallelogram. This is shown for only 3 dimensions, but let's suppose that we've extended this concept to 4 dimensions. This term in Einstein's field equations can then be computed as There is only one term remaining on the left-hand side of the equation that we've not yet talked about. This is the cosmological constant governing the rate at which